In this lecture, we want to talk about properties of unique factorization domain. So first we start with the definition of associates. So say we are given two elements of a ring R1 and R2. So R1 and R2 are associates if they differ by a unit. So that is R1 is equal to U times R2. This U is a unit. So this U is a unit. So R1 and R2 are then said to be associates. So now we come to the definition of unique factorization domain. So this unique factorization domain has three things. One, it is a domain, integral domain to start with. Number two, it has a factorization. And number three, this factorization is unique. So it is an integral domain in which every non-zero element, say R in our R, so you fix this UFD or unique factorization domain as R. It has two properties. So the first property is you can do factorization. So R is U times P1, P2 all the way to Pn. So this U is a unit, where U is a unit, and each of these Pi's are irreducible. Number two, this factorization is unique up to associates. So what does this mean? So say you have this R, you can factor it like this. Say you have another factorization of R, where V is a unit, and now you have Q1, Q2 all the way to Qm. So first thing is that number of these factors are equal. N is equal to M, and then each of this Pi is an associate of Qi. So that is Pi differs from Qi by a unit, just like here. So there is some unit which you multiply to one of the elements, you get the other one. So we have already verified these two properties for PIDs. So in the lecture on principal ideal domain, we verified these two properties. So the first example of a UFD is a PID. So every PID, that is a principal ideal domain, is a UFD, that is unique factorization domain. And this inclusion is strict. So PIDs are strictly contained within UFDs. So an example we will give is that this ring of integers, and you attach to it x, so that is the polynomials with integer coefficients, this ring Zx. This is a unique factorization domain, but not a PID. So you can see that this is not a PID because you have an ideal, this 2 comma x, this lies in this Zx, but this cannot be generated by a single element, and therefore this is not a PID. So Zx, this is not a PID, simply because you cannot generate this ideal with a single element. Another example, number 2, is a field is also a unique factorization domain. So the big theorem we want to prove is this: if R is given to be a unique factorization domain, then this Rx, that is ring of polynomials with coefficients in R, is a unique factorization domain. So if R is a unique factorization domain, then you can simply not worry too much about the polynomials with coefficients in R. That will also be a unique factorization domain. But to prove this theorem, we have to prove a couple of results. So first, let us define primitive polynomial. So a polynomial over a unique factorization domain whose coefficients have greatest common divisor 1. So that is, you just have a polynomial, but its coefficients do not have any factor in common. Obviously 1 will be common factor, but other than 1 there is no common factor between the coefficients. So if you have such a polynomial, it is called a primitive polynomial. So this we are going to use. So let us first prove this result, this proposition. Non-zero element in a unique factorization domain is prime if and only if it is irreducible. So primes and irreducibles are the same in a unique factorization domain. So in the lecture on PIDs, we showed that a prime is irreducible in an integral domain. So by definition, a unique factorization domain is an integral domain. So therefore prime is irreducible. Prime implies irreducible or is irreducible in unique factorization domain. So now we have to do the other direction. So what we have to show is, so say you have a P which is irreducible, and you assume that P divides AB, then we want to show that this P is prime. Therefore you have to show that P divides A or P divides B. So you start with P divides AB. So P divides AB you can rewrite like this. That is AB is equal to P times C, where C is some element in the ring. Now since we are working in a unique factorization domain, this A and B have a decomposition like this. So A has a decomposition like this, B has a decomposition like this, and you have this irreducible on this side. So since this decomposition is unique, so you have a unique decomposition of A or B in irreducibles, we know P will be associate of some irreducible factor of either A or B. So say P is an associate of some irreducible factor, say Qi, and Qi is irreducible factor of say A. So that is A, say, decomposes as this is a unit, V is a unit, and then Q1, Q2 all the way to Qi to Qm, and all these are irreducible. All these are irreducible. And we are saying that say P is associate of some Qi, so you can write Qi as U times P. So instead of Qi you plug in UP right here. Everything else you copy the same. So A is now equal to this entire factor, and you can see P is living right here. So P divides A, and that's what we wanted to show. We wanted to show P divides A or P divides B. So we just took an associate, P as an associate of some factor of A, and that just shows that P divides A. So we are done. This is done. So we have shown that irreducible is prime in UFD, and prime is irreducible, so you have equality. So number 2 we want to show is this: a product of primitive polynomials is primitive. So say we are given two primitive polynomials, f of x and g of x. So this is primitive polynomial like this, a n xn, a n minus 1, xn minus 1 all the way to a0. And you have a polynomial gx which is bm xm plus bm minus 1 xm minus 1 all the way to b0. So the way we think of primitive polynomials is that their coefficients do not have any factor in common except 1. So their greatest common divisor is just 1. So say you have a prime p, you pick up an arbitrary prime p. So say this prime p divides a0, it might divide a1, a2, a3, but at some point in time it will not divide a particular coefficient, because if it ends up dividing all the coefficients, then all the coefficients will have this prime p as in common. So we are going to use this property. So if prime p divides some a0 or a1, at some point in time it will stop dividing the coefficients. So now if you multiply f of x and g of x, you start doing polynomial multiplication. So you know that coefficient of xi plus j will be say ci plus j, which will be ai bj. So this obviously these coefficients should add up to xi plus j. These two add to I plus j. Similarly, you will have coefficient of ai plus 1, bj minus 1. Again, this adds up to I plus j, and so on. So all these are coefficients of our polynomial, which you obtain by multiplying f and g. So now we come to the proof. So since we have these primitive polynomials f and g, so these are primitive polynomials, you take some prime p and say this prime divides maybe some of the coefficients. Then this prime would not divide some ai, and this prime would not divide some bj for I and j largest. So because if this prime ends up dividing all these factors, then this will no longer be a primitive polynomial. Similarly, if the prime ends up dividing all the b's, it will no longer be a primitive polynomial. So there exists some I and j, and you take these I and j as the largest ones. So this prime p does not divide ai, it does not divide bj, so therefore it will not divide ai times bj. So it will not divide this. So if the prime does not divide this, it will not divide ci plus j. So prime will not divide ci plus j. So it does not divide the coefficient of the polynomial obtained from the product of these two factors. So since we are talking about arbitrary prime, the product is also a primitive polynomial, because this prime will again not divide the coefficient obtained. So a product of primitive polynomials is primitive. So number 3 we want to prove is that if you have a unit in R, this will also be a unit in R of x. So say you start with u as a unit in R. So if u is a unit in R, then obviously there exists another v in R such that this uv is 1 in R. But then this uv will also be 1 in R of x. So you still have u as a unit. So number 4 we want to prove is that a prime in R is also a prime in Rx. So for this we will use the contrapositive definition of prime. So suppose P is prime in R, we want to show it is prime in R of x. So we need to show if P does not divide F and P does not divide G, this implies P does not divide Fg. So notice that our usual definition is if P divides Fg, then this should imply P divides F or P divides G. So now you take the contrapositive of this, and that is precisely this: P does not divide F, and or becomes and P does not divide G, and the implication reverses: P does not divide Fg. So we are going to proceed in the same way as we did in number 2. So you take two polynomials f of x and g of x. So f of x looks like this and g of x looks like this. So P does not divide f and P does not divide g. So this is given to us. So if P does not divide f, there must be some coefficient here which P does not divide, and there must be some coefficient here which P does not divide. So pick ij greatest such that P does not divide, say, a coefficient here ai, and P does not divide a coefficient here, say, bj. Then P will not divide this coefficient ci plus j, which you obtain. So this ci plus j is coefficient of xi plus j. So this you obtain by multiplying these two polynomials. So you obtain a new polynomial, and ci plus j is a coefficient of xi plus j. You can see these indices add to I plus j, this I plus 1, j minus 1, this and this. So all this add up to I plus j. So P does not divide ai, P does not divide bj, so P does not divide this. So therefore P does not divide this. So P does not divide ci plus j. So thus P does not divide the entire polynomial here, because this entire polynomial obviously contains this factor ci plus j here. So P will not divide this. So P will not divide the product. So this is the product of f times g. So we have shown that P does not divide f times g. So now we want to prove number 5. So say you have a primitive and an irreducible polynomial like this, f of x in R of x. Now if you start with the primitive and an irreducible polynomial, it will become prime. So to show this, we will have to pass on to the field of fractions of R. So you start with R and then you will pass on to field of fractions of R, which we will call as f. So say you start with this: f of x divides g of x times h of x. So to show this is prime, then you have to show that f of x divides either g of x or h of x. So we are going to show that f of x divides g of x. So you start with this in R of x. So then this f of x will also divide g of x times h of x in this bigger ring f of x, where f is a field. Now f is the field of fractions of R. So it is important that we pass to this bigger field, because now we can use this fact. So this f of x is a PID. So you adjoin x to this field f, it is a PID for f a field. So for a field, so for example, you adjoin this rationals x, this is a PID, then this is a PID, adjoin x to complex numbers. So given any field, you adjoin x to x, you get a PID. But we have already shown in principal ideal domains, irreducibles are prime. So since now you already know that you started with f of x as primitive and irreducible, it is prime for field f. So in this bigger f of x, we know that f of x will divide either g or h. So this f is going to divide g or h. So say without loss of generality, it ends up dividing g. So ends up dividing g, that means in this fx you can write g is equal to fk, where k lies in here. Now you break everything in primitives. So we started with g and f originally in R of x, so you should break them into primitives. So you write g as ag1, where this g1 is primitive, and you also break this k into primitives. So k you can write as b over, say, k1. This is primitive. Now we are writing here as a fraction because this k lies in this, the coefficients are in the field, so you write as a fraction to take something common out so that you have a primitive here. G we did not have to worry about because G you started with in R of x, so you had f, g and h, all of them lied in R of x to start with, so we just have a here. So now what we do is you take this equation g equals to fk, and for g we plug in this, which is this here, and for k you plug in this here, so you get b by c k1, and f you keep as such. So now clear the denominators. You have ac g1 is equal to bf k1. So k1 is primitive, g1 is primitive, and f is primitive to start with. So we said primitive and irreducible f. So f is primitive and irreducible. So again notice that product of these two primitives will give you a primitive. So you have a primitive here, you have a primitive here. So now these two are primitive. So if you go from this R of x back to R, then that means that AC is associate of B in R. So in R you will have AC as associate of B. So if you forget these primitive polynomials, so therefore there is a unit V, so that AC is associate of B, so you can write B as VAC, where V is the unit. So now coming back to this equation, so instead of B you write VAC. So instead of B you write VAC. You cancel this AC with AC, you get G1 is equal to this V right here, and then you have FK1, and you have FK1. So instead of B you write it VAC. So everything here. So this equation you write here. So this implies now G is equal to AG1 from here. You copy this down. Instead of G1 you write VFK1. So you have VFK1 here. This A is sitting right here. So now you can see this entire thing is equal to G. So you can see that now this F will divide G, and that's what we wanted to show. Therefore F is prime. So F divides G times H, and we have shown now then F divides G, therefore F is prime. So now we prove this big theorem. Call this 6. If R is a unique factorization domain, and if you make a polynomial ring out of it, that is also a unique factorization domain. So we are going to use an important fact. Say you have a field F, and from there you make a polynomial ring out of it, then this polynomial ring will be a PID. And PID is a unique factorization domain. So this will be a unique factorization domain. So therefore we can do factorization in this bigger field. Also, since this is a PID, irreducibles are equal to prime. So we start with a polynomial in R of x, and we have to show that this will factorize. So this will factorize something like this. So we have to show that this is units and the rest of these are prime. Just like here, you have unit and you have prime, and then we will be done. So what we do is we pass on from this R of x to, from this ring R to the field of fractions of R, call that F. So you are moving from this smaller ring to a bigger ring where F is a field, and F is formed by taking all fractions in R. So now you have moved on to a bigger field, and here in this bigger field irreducible is prime. So there are some irreducible factors for F, and you're taking irreducible factors, you just take them as primitive by taking out any common factors which might be in the coefficients. So you can take GI as primitive polynomial. So these primitive polynomials are in R of x, and therefore they are prime from here. So primitive polynomial and irreducible in R of x is prime. So you might it might seem like we are moving from gi in f of x to R of x, then how they are prime, because here it says primitive and irreducible in R of x is prime in here. Now this is because in this proof of the theorem we showed that you took this primitive and irreducible polynomial and passed on to a bigger ring f of x, and then we showed that it was, when you came back to R of x, it was still prime. So these gi will also be prime in R of x. So you do this factorization like this, but since we are doing this factorization in f of x, you have a fraction here. So the next thing we do is we get our primitive polynomials. So you write this as af1, where f1 is primitive. So we can clear the denominator. You can write as f1 as r, g1, g2 all the way to gk. So these are primitive polynomials. This is a primitive polynomial. So if you get rid of these polynomials, all these are primitive, then this as and r, they are lying in ring R. So now we are working in ring R. So as is associate of r. So r you can write as uas, where u is a unit. So because all the rest were primitive polynomials. So since these are primitive polynomials, the remaining elements have to be associates with each other. So again what we do is we write, instead of r, now you write this relationship uas. So cancel out our s. So you cancel out s. af1 you can again write as f. So this was f. So this af1 you write as f, and on this side you have ua is remaining and rest of your primitive polynomials. Now this a we can factorize further, because this a is an element of our ring R, and R is a unique factorization domain. So you can write a as this b as a unit, and each of these elements ai are prime. So you get a factorization like this. So instead of a, this a, you plug this in here, and this v goes here. So you have units, and here we are saying each of these ai are prime, and we said this gi's are primitive polynomial, so primitive and irreducible, and therefore they are prime by this. So this is also prime. So this is prime and this is prime, and this is precisely what we wanted to show. We have been able to factorize f as some unit and then product of some primes.